All right, this is day 8 synthesis, part 2. Sorry for the weird lighting. Um, so we just had that really wild molecule in the screencast, and it looks something like this. So there's this like ring with an S in it and an N, and there's a chlorine, and there's this double bond right here, and then there you go, something like that, and there's a double bond right here, and then there's a carbon, and there's a H3. Okay, so one important note about interpreting formulas like this, like these are called structural formulas, because they show the structure of a molecule in a way. But they also show you what elements are present, so that's what makes it sort of a formula as well. So the thing is that sometimes we get molecules that are really, really big, like they look sort of like this. Okay. And chemists don't want, and you won't want, to draw the element that's present there, or the atom that's present there, and there, and there, and there, and there, and there, and there, etc. You don't want to draw all those atoms because it gets really tedious. So in this type of formula, every intersection represents a carbon atom. That's just the simple thing for right here. Okay, so every intersection point that doesn't have another element written is a carbon. So like this right here is a carbon. This right here is a carbon. This right here is a carbon. Okay, there is also a carbon over here, but that's fine. This carbon it was a choice by the person who made this structural formula and wrote it this way to write the C there. They could have also written it simply by doing that and just having a line that goes off of the end like that. And the reason for that is that there's like a rule that I'm definitely not expecting you to remember, but I'm going to give it to you now so that you can apply it today, and you'll this may help you figure out how to sort of disassemble or like make sense of a molecule. It's called by some people the honk 1 2 3 4 rule. Honk 1 2 3 4. And if you think back to the video with Tyler DeWitt, where he was showing you the periodic table, something like this, right? Something like that. And he was showing you that elements that are in this first group have 1 valence electron. Elements in the second group have 2 valence electrons. Elements in this group over here have 3, 4, 5, not gonna fit, 6, 7, and 8. Okay. These valence electrons tell you about how many bonds that substance is likely to make. Okay, hydrogen is over here in the periodic table. It has 1 valence electron, and so it's likely to make 1 covalent bond. Okay, carbon, on the other hand, is in this group right here, and so it has 4 valence electrons. And as you probably noticed in the collisions game, carbon has 4 valence electrons, and so it can make 4 single bonds. Okay, you might have also noticed that nitrogen, it has 5 valence electrons, but it's energetically stable when it has 8 valence electrons. So it is energetically favorable for the nitrogen to gain 1, 2, 3 valence electrons through bonding. And so you might have also noticed that in the collisions game, that nitrogen will want to share 3 electrons to help it become as energetically stable as possible. But so, like, the simple rule that I think of that helps me remember, and this may help you in organic chemistry in college, who knows? I've known some people who've taken OChem in college, and they're like, no one ever taught me the Hunk 1, 2, 3, 4 rule, but it makes so much sense. So you can just remember, hydrogens are going to make 1 bond, oxygen will make 2 bonds, nitrogen will make 3 bonds, carbon will make 4 bonds. And so let's do a bonding number audit on this molecule right here really quickly. Okay, our oxygen right here has 2 bonds. Cool. Chlorine doesn't fit that rule, so we're not going to worry about it. Sulfur doesn't fit that rule, so we're not going to worry about it right now. Nitrogen should make 3 bonds. And so here we see nitrogen has 1, 2, 3 bonds. Okay, cool. But what about these weird carbons? There, and there. And then what's going on with this? Okay, so this is some chemistry shorthand again that I want to tell you about now so that you expect it when you're looking for your molecules on Google. So one thing that chemists do is they don't write all of the hydrogens, because hydrogens can make 1 bond. They're really handy if, well, I shouldn't say that. They need 1 bond, and they have 1 electron to give, and there's really small atoms, so they can get in and out of a lot of places. And so they bond in a lot of different places. And so chemists don't want to always draw all of the hydrogens that they would need to draw, because that would be a lot. And what ends up happening is that oftentimes when you have a carbon atom, the other atoms that are present on them are hydrogen atoms. So what's over here, actually, get a different color. This is a carbon atom right here, this intersection, but actually there's also a hydrogen there. It's just not drawn. It's assumed that because you only have, oh, actually, no, sorry, that's incorrect, because there's a double bond right here. My mistake. I should have followed the Hunk 1, 2, 3, 4 rule first. 1, 2, 3, 4. So this this carbon already has 4 bonds, so it's good. This one has 1, 2, 3 bonds shown. So to make that 4th bond, that's where we would add a hydrogen there. So there is actually a hydrogen bond right there. This carbon has 1, 2, 3, 4 bonds. So it does not have any sort of hidden hydrogens that are not being shown. If we go around, just do an audit of all our different atoms. So this right here, it looks like it's just like a stick, right? But this is actually showing that there is an unshown carbon right here. And because we don't see any, because we only see 1 bond, but we know carbon makes 4 bonds, that actually means that there's 1, 2, 3 hydrogens bonded to that carbon. Okay. Pause and digest this if you need. This is a lot of information. This is like understanding chemical structures 101. But the last thing to show you is that some of you are going to end up seeing molecules, and actually we're all going to see molecules like this on day 9. So I want to show you this anyway. If you see a molecule that has a long section like this, it is especially important to remember this idea that these 2 things. 1, the carbon atoms are not being shown as carbons in so many cases, but all of these are carbons. The reason they're carbons is because they're not specifically said to be something else, right? If this was a sulfur, you would see an S. If it was a chlorine, you would see a Cl. But because you just see a point, you assume it's a carbon. Carbon is everywhere, okay? And because carbon should make 4 bonds because it has 4 valence electrons, each of these carbons should have 4 bonds. And so this one has 2, so it's going to have 2 hydrogens. Hydrogen, hydrogen. Okay. This one has 1 bond currently, so this is going to have 1, 2, 3. Hydrogen, hydrogen, hydrogen. Okay. Hopefully this is resonating with patterns you noticed in the collisions game. But so what you see here is that there's a ton of hydrogens, and that if we actually drew all of them, you can start to see how messy it gets, honestly. Like, there's so many hydrogens, and it's so hard to see what you want to see if you're spending time counting all the hydrogens. So this messiness that you're seeing now is the reason why chemists don't write in the C or all the H's in so many cases, and they just simplify it by drawing those simplified structures. Sometimes you'll see those called, or you'll hear of them as being called skeletal structures. Just because they look kind of like skeletons. Okay. Okay, so this was a lot of information, but the two big ideas that I want you guys to make sure you look out for are: one, look for carbons that are there, but which are not shown with a C. That's the first thing. Second, look for hidden hydrogens. Okay, these hidden hydrogens are going to be there.